Hello everyone. My name is Sai Kumar, Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So this course is an introductory course to Computational Fluid Dynamics, which is for final year students of Aeronautical Engineering. So to begin with, let us start with the first topic of this course, which is Introduction to CFD. So today we are going to discuss about the various approaches to solve a fluid dynamic problem, and followed by CFD. What is CFD? And then why most of the organizations are using CFD as a tool to solve the flow problems. Then we will try to understand what is the CFD process. So let us begin with the first topic, which is types of approaches. So basically, to solve any fluid flow problem, we have three approaches. The first one being theoretical or analytical approach. Then we have experimental approach, and the last we have computational approach. So these three are the basic approaches which we can categorize to solve any fluid flow problem. Now, coming to theoretical approach, it is the basic of all the approaches where the theory is used to prepare mathematical models or to create mathematical models based upon the physics of the problem. So these mathematical models generally are set of equations which relate the fluid variables, and will try to understand or predict the behavior of fluid by understanding the variations of one parameter on the other parameter. So this approach is very much limited to simple conditions, which are almost like ideal conditions, whereas we cannot apply this theoretical approach to complex shapes, complex geometries, or in the problems where there are a lot of complexities involved. So the basic advantage of this particular approach is that we have exact solution for very simple scenario. For example, if we take what is the mass flowed through a pipe, or what is the amount of water that is flowing through pipe, so we can easily predict that using this theoretical approach. So it offers a basic understanding of fluid behavior and the fundamental concept behind the physics of the problem. The major limitation is you cannot solve difficult problems. That is, it is very idealistic situation. So due to that, the real solution of the problem is not possible with theoretical approach, because you have lot of constraints to the mathematical model what you consider. So because of that, you have lot of limitations to the calculations which are almost like there will be a deviation with the real-time scenario, especially in case of complex problems. Now let us move to experimental approach. So the name itself indicates that we use experiments to conduct or study the flow behavior. So we create a controlled environment using a test facility where we study the fluid behavior. So the experimental approach involves physical testing of the scenario based on the observations which are being carried out at the testing facility. We predict the behavior of the flow. So this approach uses specific equipment, and for every specific problem you need to have a specific setup for conducting the or creating the environment. So some of the examples of those specific equipments are wind tunnels, water channels, and we use pressure sensors for the measurement of pressure over the bodies. That is how we take the readings or take the data from the experiments and try to analyze that and generate certain conclusions. So the major advantage of this particular approach, experimental approach, is that you have real world data. The data whatever we gather or we obtain through these experiments is very much accurate, or which is very much close to the reality. Then we can validate the results which we predict using theoretical approach or computational approach, because they are very much real when compared to the scenario. The major limitation is cost, that is very much expensive, because the equipment is limited to only certain kind of scenarios. So for every type of fluid problem you have to change the equipment itself, so the cost will be very high. At the same time, the operating cost for these equipment is very high. And another limitation is time consuming. For testing using experimental approach, you need to create a prototype. At least the test specimen has to be produced. So this causes very much time delay in the process of conducting experiment, as well as in process of evaluating the flow behavior. And one of the major drawbacks of experimental is the instrumentation. So the accuracy of instrumentation is the limitation of the measurement. The precision of measurement will depend on accuracy of the equipment. So to that extent, there are a lot of round of errors in that. And one more limitation is that the ability to scale the models. So size of models is very much constrained in the experimental approach. Now let us move to the third approach, which is the computational approach. It is also called as computational fluid dynamics for the fluid flow problems. So it uses numerical methods and algorithms to solve fluid flow problems. So basically whatever mathematical models are there, those mathematical models will be solved using numerical methods which are discretized, then solved using a specific algorithm to follow a specific sequence of steps for solving those numerical values. So the major objective of CFD is to model continuous fluid flow models, which will be defined using partial differential equations, and these equations will be solved using numerical methods. As I mentioned, we will be using numerical methods to solve these partial differential equations. So basically we can call these partial differential equations as the mathematical model for the numerical methods, which involve solution for the fluid flow problems. So the solution is obtained by solving these set of the equations through space and time marching process, which will be defined by the algorithms. So CFD as an approach, so you can say, since CFD uses theory as well as concept of experimental, we can call or we can consider CFD as combination of these two, theory plus experiment. So the basic fundamental theories can be used to develop the mathematical model, and the experimental setup can be virtually created using those mathematical models, so that we can solve the fluid flow problems. So CFD can be called as a virtual experimental setup to solve the fluid flow problems. So let us see why we have to choose CFD. So before we go to why choosing CFD, since CFD purely depends on the mathematical models which are generated from the theory, so CFD can only complement theory, but it cannot replace any of these two approaches, that is theory or experiment, because experiment results will create a real-time scenario, but CFD, since it does it in virtual environment, it has lot of drawbacks. That is primarily the main thing is the slight deviation from the real time scenario, whereas experiment gives us exact real time scenarios. So since it fundamentally depends on the mathematical models developed using theories, but the results are not that much sophisticated when compared to experimental approach. Hence, CFD can complement these two as an alternate, but it can never replace these two approaches. So with this, let us continue with why we always use CFD. So CFD can handle any type of complex geometry. First of all, CFD can handle any type of complex geometries. So it can be an aircraft, it can be a component of engine. All those can be handled in CFD. You can simulate them, and low cost, because since we are creating everything in virtual environment, there is only need for a particular hardware, that is a computer with specific RAM and other configurations, which is more than enough with a specific CFD software to solve the fluid dynamic problem. Next, high computational speed. See, due to advent of the high speed computing, the computational process is very much high, reducing time for both creating a prototype, fabricating it and testing it in experimental setup. So it reduces all the time. So hence the process will be very much fast in CFD when compared to experimental approach. And coming to linearity of the problem, since any complex problem can be solved using CFD, there is no proper restriction for linearity of the problem, provided we have that infrastructure, that is the capability, computing capability is there, then linearity shouldn't be a problem for solving any kind of fluid flow problems. So the major drawback with CFD is errors. So whenever we discretize, whenever we try to use numerical methods, always accompanied with certain errors. So these errors are common, so naturally that will lead to slight deviation from the realistic solution or the actual solution. So the primary drawback of CFD is that there will be slight deviation in the actual solution. That is because of the numerical method what we are following. So when it comes to experimental, the major problem is the scaling problem. So the size of the equipment has to be in according with the size of the problem. So since that is not possible, we have to scale the objects or scale the models. So scaling will be a major challenge in experimental approach. And other aspect is difficulty in measurement, the accuracy of measurement system, the precision of measurement system, and the errors, if there are there, then that will be a major problem with measurement in experimental approach. Then high operating cost, which will be, again, since these use lot of machinery is involved in experimental setup, they occupy large equipment, since they occupy large spaces and they require huge power to operate them. So it will be occupying lot of space, as well as it requires lot of power and requires high operating cost to conduct experiments for solving the fluid dynamic problem. So theory, it is very much restricted to very simple geometries. Only simple problems, linear problems can be solved. Other than that, the complex problems cannot be solved in theory. So now let's understand the process of CFD. So CFD as a process involves three phases: preprocessor, next solver, then postprocessor. So preprocessor basically involves, the first step is understanding the physics of the problem. So until unless we understand the nature of the problem, we cannot decide what type of equations are involved. So what are the relation between any two parameters of the flow? So we try to decide the parameters based on the physics of the problem. For example, if you take flow through a constant area pipe, since area is constant, I can neglect the area as a variable. Same thing if I consider a nozzle. Since area is changing, area also will become one of the important parameters for me while evaluating the problem or while trying to analyze the problem. So understanding physics of the problem is very much important, wherein you can neglect certain terms or parameters which have least influence on the behavior of the flow. At the same time, if we understand the problem, then only we can develop the boundary conditions for that. Based on the boundary conditions, the solution will proceed. Next is mathematical model. So once we identified the problem, once we understood the problem and identified the variables what are involved, we try to develop a relation between variables. So these relations between variable will be in mathematical form. Hence, these relations we call them as mathematical models. So we have to develop mathematical models. Based on the mathematical models, we consider the numerical methods what we follow. So once we are done with identifying the mathematical model, once we develop the mathematical model, we need to understand the nature of the mathematical model. So based on the nature of the mathematical model, we'll try to discretize the given equation, that is the mathematical model. So we discretize it. So discretization will be one of the important aspects of CFD, because as we know, all the numerical methods are computed or carried out at discrete points. So discretization is the process of generating those discrete points where the numerical methods can be implemented. Once the discretization is carried out, then we set out to solution model. So what type of solution model has to be there? So that will be based upon the discretized equations. So discretized will always have the equation. So what scheme you are using to discretize, that will be considered in the solution process. So whether we are following forward time, central space, or we are considering first order of equation, second order of equation. So these kind of things will be discussing or will be considering in the preprocessor phase. Then we have solver phase. Once we develop the equations, we select the appropriate solution procedure. So what should be our direction? Sure, if it is time, so time we always go for forward time. Time is always in forward direction. Space can be central, forward, or backward. So which scheme you are generally employing, followed by what is the approach, what type of equations you are using. That is, are you using pressure linked equations or coupled equations? That will be based upon the, again, the physics of the problem. So which equations you are using, or basically these are nothing but algorithms. To be precise, these are the algorithms which you are using to solve these numerical models. So once we are done with selection of that algorithm, Then we precisely move to the boundaries. We specify the boundary conditions and we start evaluating for these specific boundary conditions. We'll start with known values or unknown values. First, we have to know what are the boundaries. So, we understand what are the boundary conditions, and based on the boundary conditions, we'll try to predict the solution. So, with that, we'll be concluding the solver where we end up with the solution of the numerical equations using algorithms and based on the values which are provided at the boundary conditions. So coming to post-processor, post-processor is the last phase of your CFD process, where whatever the results we obtain after calculating, those results will be verified, or will be evaluated for the further process. That is, we need to understand, let's say, flow behavior around the body, wake formation around the body. So we can predict that using streamlined nature of the object. We can plot vectors. We can look at the contours to predict how the parameter is varying throughout the flow domain. So once we have proper understanding of that, we end up with the solution. We end up with the certain conclusions. Based on the conclusions, we will be validating the results using experimental approach to finalize the configuration. So this is about the CFD flow process. So CFD process. So this is what we have discussed today, that is types of approaches to solve a fluid flow problem. Then we have CFD, what is CFD and why it has been widely used in most of the organizations to solve fluid flow problems. Then we have discussed about CFD process. So that's all for today. Thank you.